Everything you own, your phone, your laptop, the internet itself, pick up a handful of sand. That becomes this. A chip no bigger than your thumbnail. It contains tens of billions of transistors. It runs billions of calculations every single second. Your photos, your messages, your payments, your heartbeat monitored in a hospital, all of it started as dirt, and almost all of it hangs by a thread. That thread leads to one island, 23 million people, around 110 miles off the coast of a nation that considers it its own territory. We'll get there. Before we follow the journey from sand to chip, we need to answer one question. Why silicon? The universe handed us 118 elements. Why does every phone, every computer, every data center on Earth depend on this one? Most materials are either conductors or insulators. Copper conducts, electrons flow through it freely. Rubber does not. Electrons are blocked completely. Both are useful. Neither is interesting. Silicon is different. It sits at a rare crossroads, right on the boundary between metals and non-metals. And its position there comes from something very specific. It has 4 electrons in its outer shell. 4, not 5, not 3. 4. That number means silicon holds its outer electrons with exactly moderate grip. Not so tightly that electricity can never flow. Not so loosely that it flows all the time. Depending on conditions, temperature, impurities, electric fields, silicon can act like a conductor or an insulator. And more importantly, we can choose which one. We can tune it, adjust it, direct it with precision. That controllability is everything. You take a tiny gate, microscopic, smaller than a virus, and put it next to a silicon channel. Apply a small voltage, a field forms, electrons are attracted, current flows. Remove the voltage, the field collapses, current stops. Open, closed, 1, 0, binary code. The language of every computer ever made, built from that one controllable property. Now imagine that happening billions of times per second. That is what is happening inside your phone right now. Every tap, every swipe, every pixel that renders. And here is what makes silicon almost unfairly good for this job. It is the second most common element in Earth's crust. Only oxygen beats it. A material that is controllable, tunable, and essentially unlimited in supply. It almost should not be possible, and in a way it is not. Because while silicon is everywhere, pure silicon, the kind we actually need, is almost nowhere. That is the problem we had to solve. Bell Laboratories, December 1947. 3 physicists, William Shockley, John Bardeen and Walter Brattain, are huddled over a small, almost comically humble device made of germanium, a strip of gold foil, and a triangular piece of plastic. They press it against a contact. Electricity goes in. Amplified electricity comes out. Electricity is the simple miracle you can hear. They had invented the transistor, a device that can both amplify a signal and, crucially, switch it on and off entirely. At the time, the amplification seemed most immediately useful. Make radio smaller, improve telephone signals. But it was the switching that would change everything. Open, closed, 1, 0. The foundation of every computation ever performed. They had no idea they had just invented the most manufactured object in human history. By the time you watch this, more transistors will have been produced than there are stars in all the galaxies of the observable universe. They shared the Nobel Prize in Physics in 1956, but the transistor in its original form was fragile and impossible to scale. Each one had to be built by hand. Wiring a circuit with hundreds of transistors was a nightmare. Thousands was essentially impossible. There had to be a better way. In 1958, 2 engineers working independently, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor, had the same idea at almost exactly the same moment. What if you did not wire components together? What if you built them all on the same piece of material and the connections were part of the chip itself? This was the integrated circuit, the microchip. Kilby built his on germanium, Noyce built his on silicon. Silicon won. Noyce's approach became the template for everything that followed. In 1965, Gordon Moore predicted that the number of transistors on a chip would double roughly every year, a rate he later revised to every 2 years. Not through magic, Through relentless compounding engineering, better materials, better tools, better processes, each generation standing on the shoulders of the last. Every 2 years, the same piece of silicon, suddenly twice as capable. Not 10% better, twice, for decades. If your car improved at Moore's pace since 1965, it would now travel at a fraction of the speed of light and cost less than $1. Transistors went from millimeters to micrometers to nanometers to angstroms. Today, the features inside the most advanced chips are measured in atoms. We are building switches counted in atoms. Then there was a company called TSMC, founded in 1987 by Morris Chang. TSMC was built on an idea that seemed almost backwards. What if a company made chips but designed none of them? Before TSMC, every major chip company did both. The assumption was that design and manufacturing were inseparable, that no serious customer would trust their most sensitive intellectual property to a company whose only business was building someone else's vision. Chang believed that assumption was wrong. He thought trust could be built over time through discipline and neutrality alone. He was right. Most people at the time thought he was not. Over the next 35 years, TSMC would quietly become the most strategically important company on Earth. But before any chip can be designed or built, the material has to be made. And making it is one of the most extreme industrial processes in human history. Silicon doesn't exist freely in nature. What we find in the ground is silicon dioxide, with silicon bonded tightly to oxygen. Breaking that bond requires industrial-scale fury. The journey starts not at a beach, but in a quarry. We're after quartzite, a dense hard rock formed over millions of years under geological pressure. The highest purity deposits are found in the Appalachian Mountains of North Carolina, in parts of Brazil, and in Norway. Purity matters because at the atomic scale, a single foreign atom in the wrong location can completely change how electricity moves through that region. Contamination measured in atoms is ruinous. The quartzite is mined, crushed, and fed into an arc furnace. Temperatures climb past 1,500 degrees Celsius. Carbon reacts with the oxygen, pulling it away from the silicon. What's left is raw metallurgical grade silicon, about 98 to 99% pure, and completely useless for electronics. In a single gram of silicon, there are hundreds of billions of atoms. 2% of those are wrong. That's billions of impurity atoms per gram. In a transistor operating at the atomic scale, that is disaster. We need 9 nines, 99.9999999% pure. In 1 billion atoms, one can be wrong. The raw silicon is reacted with hydrogen chloride to form a gas, CV, distilled again and again, each cycle stripping out more impurities. The process ends with ultra-pure silicon depositing onto heated rods inside a reactor. 9 nines. We're there. But it's still not enough. Purity is not the same as perfection. This polysilicon is made of millions of tiny crystals pointing in different directions. Random orientations and random boundaries scatter electrons. They cause interference and they introduce errors. We don't just need pure silicon, we need one crystal. Trillions of atoms, all in perfect alignment. We melt the polysilicon in a quartz crucible at 1,414 degrees Celsius. Then we take a tiny seed crystal and lower it gently to the surface of the molten material, and we begin to pull it upward. Slowly, carefully, rotating it as it rises, atoms attached to the seed. Because they are attaching to a template that is already perfectly ordered, they lock into exactly the same alignment, layer by layer, one atom at a time. This process takes between 24 and 48 hours per crystal. Any vibration, any temperature fluctuation, any contamination and a defect will propagate through the entire structure. What emerges is a massive cylinder of silicon, a boule, a single crystal, typically 300 millimeters in diameter, about 1 meter long, one crystal, trillions of atoms, perfectly aligned. It is one of the most perfect large-scale objects ever manufactured by human beings. It's sliced into hundreds of wafers, each less than 1 millimeter thick, then polished, not just smooth, but atomically flat. surface variations of less than a nanometer across the entire disk. A nanometer is about the width of 10 hydrogen atoms lined up side by side. All of this, and we have not made a single transistor yet. We've only prepared the canvas. A semiconductor fabrication plant is the most precisely controlled environment ever built by human beings. Temperature, humidity, vibration, electromagnetic fields, chemical purity, all controlled to tolerances that would have seemed like science fiction 60 years ago. In a hospital operating room, the air contains around 350,000 particles per cubic meter. In the clean rooms where leading-edge chips are made, the air is millions of times cleaner than that. Humans are the biggest threat. Every hour, the average person sheds around 30,000 dead skin cells. We breathe, we sweat. We are, from the chip's perspective, walking contamination events. Everyone who enters wears a bunny suit, a full-body garment covering every inch of skin, gloves, hood, booties, a filtered mask. The suit isn't to protect the worker, it's to protect the chip from the worker. Now, what actually happens in there? The goal is to build, layer by layer, a three-dimensional structure of impossible complexity. Transistors, wires, insulators, connections, all stacked on top of each other, each layer precisely aligned to the ones below. The key step is photolithography. We use light to print a circuit pattern onto the wafer, but not visible light, not even conventional ultraviolet light. Extreme ultraviolet, EUV, a wavelength of just 13.5 nanometers, roughly 28 times shorter than the shortest wavelength the human eye can detect. You cannot print a feature smaller than the wavelength of light you are using. To build transistors measured in nanometers, you need light measured in nanometers. Generating EUV light requires something of staggering, almost incomprehensible complexity. The machine that does this is built by a single company, ASML in the Netherlands. No American company makes these. No Chinese company has yet built one capable of manufacturing chips. No Japanese company. For now, ASML alone builds the machines that make the world's most advanced chips possible. Each EUV machine costs upward of $200 million. Inside, a laser fires at tiny droplets of liquid tin, about a third the width of a human hair. The laser strikes each droplet twice, a pre-pulse that flattens it into a disc, then the main pulse at full power. The tin explodes into plasma superheated to more than 200,000 degrees Celsius. Roughly 40 times hotter than the surface of the sun. This happens 50,000 times per second. Each explosion emits a burst of extreme ultraviolet light, captured and directed through a series of mirrors, not lenses, because EUV light is so energetic it would be absorbed by any solid material. And every one of those mirrors is the most precisely manufactured object ever made by human hands. Here is how precise. If you took one of these mirrors and scaled it up to the size of Germany, the tallest surface irregularity would be less than a millimeter high. Sit with that for a moment. An object the size of a country, smooth too, within a millimeter, everywhere. That is what it takes to direct light at this scale. The light passes through a mask containing the circuit pattern projected onto the wafer and reduced to a fraction of its original size. Where the light hits, a chemical reaction occurs in a coating on the wafer's surface. The exposed areas can be washed away. The protected areas remain. The wafer is etched. The pattern remains permanently in the silicon. This sequence repeats over 100 times for the most advanced chips, each layer precisely aligned to the ones below. A city built upward, layer by layer. But circuit patterns alone are not enough. To build working transistors, we need to give specific regions of the silicon a fundamentally different character. This process is called doping. Imagine a silicon crystal as a perfectly arranged auditorium, every seat filled with exactly the right person. Now we fire a beam of ions, individual atoms that are electrically charged and accelerated to high speed, directly into the silicon surface. Fire in phosphorus or arsenic atoms, each with one more outer electron than silicon needs, and you're adding extra people with nowhere to sit. They wander freely, These free electrons become charge carriers. N-type silicon fire in boron atoms which have one fewer outer electron, and you leave empty seats. Other electrons shift to fill them, and the holes move in the opposite direction, behaving like a positive charge. P-type silicon. Put an N-type region next to a P-type region. At the boundary, electrons and holes meet and cancel each other out, creating a thin zone with no free charge carriers. A depletion zone, an invisible wall inside the silicon. Because the two sides have opposite charges, this wall only lets current through in one direction. You have made a diode. Now add a controlling gate just above that junction. Apply a voltage to the gate. Its electric field reaches down into the silicon, collapses the depletion zone, and current flows. Remove the voltage. The field disappears, the wall rebuilds, and current stops. Open, closed, 1, 0. You have made a transistor. Not a vacuum tube, not a hand-wired component. A transistor whose gate is a few nanometers wide, surrounded by 100 billion identical neighbours, each switching on and off trillions of times per second. 100 billion switches in an area the size of your thumbnail. When manufacturing is complete, the wafer is tested. Thousands of patterns run through every circuit. Some chips will fail. A microscopic defect, a misalignment, an iron one atom off. Failed chips are marked, then discarded when the wafer is diced. Working chips enter the world, in phones, in laptops, in cars, in satellites, in pacemakers, in the servers that power every website you have ever visited. In everything. And this is where things start to break. At every single step of everything we just walked through, there are only a handful of companies capable of doing it. Sometimes just one. And those companies are concentrated in a few countries, a few cities, a few buildings. That concentration has become one of the most dangerous geopolitical vulnerabilities in modern history. EUV lithography requires machines built by ASML. Only ASML. A single Dutch company in a mid-sized city called Veldhoven builds every EUV system in operation anywhere on Earth. If ASML stopped shipping tomorrow, the world's ability to manufacture cutting-edge semiconductors would collapse within a year. One company, one city. The entire frontier of human computing capacity. At the leading edge, the chips at the frontier of what is physically possible, one company manufactures roughly 90% of global supply. That company is TSMC. Apple, Nvidia, AMD and Qualcomm design their chips, but they do not make them. Building a leading-edge fab requires tens of billions of dollars and decades of accumulated process knowledge. So they send their designs to TSMC. The chip in your iPhone is made by TSMC. The GPU powering AI is made by TSMC. The processors in the world's fastest supercomputers are made by TSMC. Across all chip manufacturing, TSMC's share is lower, but at the leading edge no one else comes close. And TSMC is in Taiwan. An island of 23 million people around 110 miles off the coast of mainland China. A democracy that has governed itself since 1949. The country the People's Republic of China has claimed as its own territory for that entire time. For decades, the industry did not worry. Taiwan was stable. The chips kept flowing. Then the world changed. In 2020, COVID-19 disrupted global supply chains in ways never stress-tested before. Chip shortages cascaded through every industry. Car makers shut down assembly lines. Millions of cars were delayed. Consumers could not get laptops or gaming consoles or appliances. The world discovered suddenly and painfully how dependent it was on a very small number of factories. At the same time, trade tensions between the United States and China escalated. The United States began restricting China's access to advanced chips and chip-making equipment. China, the world's largest importer of semiconductors, began investing billions in domestic alternatives. And one question became impossible to avoid. What if something happened to Taiwan? Chang and other industry observers have noted that in any scenario where Taiwan's connections to the outside world were severely disrupted, through blockade, military action or political crisis, the ability of TSMC to operate would be compromised within weeks. Not because factories would be destroyed, but because TSMC requires a constant supply of specialized gases, exotic chemicals, and precision parts from suppliers across the United States, Japan, and Europe. Cut those lines, and the fabs stop. Smartphones stop, laptops stop, cars stop, medical devices, defense systems. Every product that depends on computation does not just slow down, it stops. The economic damage would be measured in trillions, and recovery would take not years but decades. You cannot rebuild a supply chain that took 60 years to develop overnight. In 2022, the United States passed the CHIPS and Science Act, more than $50 billion for domestic semiconductor manufacturing. Intel announced major new fabs in Ohio and Arizona. TSMC announced a fab in Phoenix. The European Union launched its own CHIPS Act. Japan subsidized TSMC to build on Japanese soil. Every major economy reached the same conclusion. We built a system we do not control around places we cannot protect, making things we cannot replace. And even with those investments, meaningfully shifting the balance will take at least a decade. TSMC has a 35-year head start. The institutional knowledge built by tens of thousands of engineers over millions of hours of trial and error is not something you can buy or import overnight. Step back for a moment. We took dirt, we stripped it, purified it atom by atom, rebuilt it into a perfect crystal, sliced it thinner than a human hair, coated it with light-sensitive chemicals, blasted it with plasma hotter than the sun, carved patterns measured in atoms, and stacked the result into a structure of incomprehensible complexity. We did this at a scale of trillions. More transistors are manufactured every second than there are stars in the Milky Way. In 1947, the transistor did not exist. Today, more have been made than there are grains of sand on every beach on Earth. We went from zero to that in the time it takes for a single human being to live a full life. Silicon limits are becoming visible. Transistors cannot shrink forever. Engineers are already building upwards, stacking chips in 3 dimensions, exploring new materials and architectures. Whatever comes next will be built on the foundation laid by 60 years of impossible engineering. And whoever controls that foundation will shape what the world becomes. We turned dirt into the most powerful tool in human history. What do we build next? And who gets to decide? If you made it this far, I would genuinely love to know. What surprised you most? The EUV machine, the geopolitics, something else? Drop it in the comments, I read everyone. And if you want to go deeper into the economics of chip making, the race between the US and China, or the people who dedicate their careers to moving atoms around, let me know what you want next. Subscribe if this kind of thing is your world. See you then.